Hello class, this is Professor Kamen, and this is your video presentation for the hot working process. So let's go ahead and get started. So what are the basics of hot working? Well, it's not simply just deforming metals at very high temperatures. So metals are worked, and when we talk about worked, we talk about they're either bent or beaten or changed in some kind of way. They're worked above what's called the recrystallization temperature. And this is a temperature that's warm enough for the metals to actually start to what's called recrystallize. And we'll talk a little bit more about what recrystallize means later. So in other words, no strain hardening occurs and cold working takes place. And you'll understand the difference between these two when we talk about our cold working process. But when we talk about strain hardening, we talk about the metal becoming a lot stronger during the process, and that's what happens during cold working. So here's your key test. If a metal is hot worked, the hardness of the metal before and after um, remains relatively the same. So relatively no strengthening occurs during this hot working process. That's the key test. So essentially, what happens is before that metal cools, the hot temperature anneals the metal and removes the cold working that would have occurred. So what this means is anytime you work a metal, it's actually going to make it stronger. And so this annealing process, which we'll take a little bit later, is where you have the metal remaining at high temperatures, which makes the metal more ductile and weaker, so that it goes back to its original strength, so that cold working has not taken place. So a little bit more detail on what happens during hot working. I mentioned annealing before. Annealing is when you kind of heat the metal for the specific purpose of softening it or reducing its strength. Okay. And typically, what happens during the hot working process is you will begin with what's called an ingot casting. And an ingot casting is when you pour metals. Usually, we're talking about different types of steel into what's called these ingot molds. And these ingot molds are really basic molds. Usually, they're in the form of some type of a rectangular shape or maybe some type of cylindrical shape. Or sometimes people call ingots anything that you just form straight from molten metal cast. They could really be just any kind of a crazy shape, but typically a rectangular shape or some type of cylindrical shape. So you go for that ingot casting, and what happens is out of that ingot casting, when the metal solidifies, you really have a relatively weak form of the metal. Now, zooming into this a little bit more, you can see this is the representation of what's called the grains or the crystals within the metal. And we'll talk about exactly what the grains or crystals are. But you can see here that these are relatively large. It's called relatively large. Here, right at the casting, you have them fairly small. But for most of the casting, they're relatively large grains or crystals. And relatively large grains or crystals really refer to a metal structure that's really weak. Okay, if you have a metal structure that's strong, you want to see these small grains or crystals throughout the entire metal. And so when your ingot is first made, when the metal is first cast into an ingot, it's relatively in a relatively weak form. So let's talk about a different hot working process. And the first and basic process is called hot working. Now you can, I'm sorry, hot rolling rather. You can tell we're talking about rolling things. Essentially, what happens is typically an intermediate form. That means there's intermediate forms after an ingot is made. You can press things into an intermediate form, and then you can feed it through these rollers. Okay, and they're just simply used to reduce the cross section of the metal. Now, you can zoom into this just a little bit closer and see the difference between something that's cold worked and something that's hot worked. Okay, something that's hot worked, you can see the metal, you can see the grains or the crystals inside the metal. Okay, recrystallization occurs, so some reorganization occurs here. These grains are elongated as it goes through the rollers, and you can see here what happens is that these crystals come out to be a lot smaller. So that actually has a stronger structure than metal does. But since annealing occurs, in other words, since there's continued elevated temperatures, those grains actually will grow to that they're about the size that they were before. So that's what we were talking about in terms of how do you know if it's hot working, if it's the same strength before as it was after about, then you know hot working has occurred because that annealing takes place, growing those crystals or grains back to their original size, making it back to about the same strength. When we talk about cold working, you'll see this is the cold rolling process. Um, but when we talk about what happens during cold working, and cold rolling is an example of that, at the beginning, the same thing happens. You can see these small crystals form, but look, they don't grow again. Okay, so those crystals or grains stay that size, and so that improved mechanical structure, that improved strength stays that way instead of it being annealed and going back to the same strength that it was before. Okay, so again, the annealing process, annealing is going to create those larger grains. So it's just indicating a weaker or softening of the material. So remember I mentioned to you those intermediate forms and that you kind of feed through the rolling process. Well, these are those intermediate forms, and these are things that can be formed typically from an ingot. So the first thing we have is a bloom, and a bloom is formed from ingots with a into a square cross section that's about 6 by 6 inches or larger. And so these are really kind of general sizes and not very specific sizes. That's why I say 6 by 6 inches or larger. And then here's an example of a bloom. So they're very, very long pieces with a square cross section. Then you have what's called a slab. And so a slab is typically rolled, so hot rolled from an ingot, or it could be from a bloom as well, but they have a rectangular cross section about 10 inches or more wide and about 1.5 inches or more so thick. So here's an example of a slab, just kind of like a long rectangular shape here, at least 10 inches wide and 1.5 inches thick. They can be as long as you want them to, but again, these are general dimensions. They can be typically this size or a lot larger. And then you have what's called a billet. A billet is very similar to a bloom. You have that square cross section, but typically a billet would just be smaller. Okay, so here we have about 1.5 inches on either side, and that's the only difference with respect to a bloom. So let's look in a little bit more detail about the rolling process. So in the rolling process, you have blooms or ingots, sometimes even slabs, are further processed in these what's called rolling mills, and there are different kinds of rolling mills. Now, this is called a two-high mill, sometimes called a two-high reversing mill. And the reason why it's called that is because whatever your intermediate form is fed through the rollers at the beginning, and then it's reversed. The rollers actually reverse their direction and it's fed back through. So here's the initial feeding, and then it's fed back through the other way. Okay, so typically used for reducing stock. That means reducing the cross-sectional area. And here, just what happens is you have this complex mechanism to reverse direction of the rotation. So you have to stop the rollers and then reverse direction. So the rollers are going this way. I'm sorry. Yeah, going this way as they fed through. I'm sorry, going this way as they fed through. And then you have to stop the rollers and reverse their direction. Now they're going this way as the stock is fed back through in the opposite direction. You have what's called a three-high mill, obviously called three-high because now you have three rollers. And what happens here is this has an advantage in that you don't have to stop the rollers and then reverse them, okay? So the rollers are continuously rolling in the direction that they're originally going. Now, stock is passed, when we call stock, we're talking about those intermediate forms that have been formed from ingot, or even an ingot can be passed through. But you haven't passed through the top two rolls, okay? Pass through the top two rolls and cross-sectional area is reduced, and then you lower that piece and pass it through the bottom two rolls, okay? And the disadvantage of this is that you have some a handling system that can be expensive, used to kind of take it through and then lower it, and then raise it, and then lower it, and so that's how that works. That's a three-high mill. You have what's called a four-high mill. A four-high mill uses a small rollers actually in contact with the material to reduce the dimension or reduce cross-sectional area. But these smaller rollers use less energy or force. But the thing about these smaller rollers is that they're a little bit stiffer. And so you need kind of like a backing roller that's help to support the smaller roller that's actually in contact with the metal. And that's what these rollers are, to reinforce the stiffness of these rollers in contact with the metal. Then another type of mill is called a tandem mill. Now, a tandem mill is simply mill stands one right after the other. And the reason why this is beneficial is that you can go ahead and work the metal in incremental stages. The working of this metal requires extremely high forces. You can't believe how much they require. And so doing it incrementally is definitely beneficial. So these are complex systems. They can adjust the rotating speeds, and they help to even the thickness and keep from fracturing the metal. So let me play this video for you.
Steel is highly resistant to shaping when it's cold, and for that reason it is generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it is fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side.
Now they'll tell you the different types of mill stands.
The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profiled for sections, beams and columns for use in construction. Mill stands have various roll arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap.
So three-high stand.
Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products, such as plate. Universal beam mills include stands with both horizontal and vertical rolls bearing on the steel simultaneously. Rolling processes are computer controlled and monitored up to 50 times per second. Despite the huge scale of some mills, accuracy to plus or minus 50 microns can be measured.
50 microns is
The
fairly
rolled
accurate.
steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch.
All right, let's keep going here. So let's talk about some other hot working processes. Now, one process is called strand casting. This is actually interesting because in this process, you can actually skip the the ingot casting process. So you go straight from the molten metal and you go directly to that intermediate form, which in this case would be a slab of steel. Let's look a little bit closer to this diagram. You have different types. Here's a type that's where the strand casting occurs vertically, and then here's a type where the strand casting occurs kind of horizontally. It bends around and occurs horizontally. So what happens if you're skipping this casting into an ingot phase, okay? So you go straight from the molten steel right here, and as you pour the molten steel here, and as it's rolled into an intermediate form, it cools. So that's what the yellow turning to red is. It cools, and then you spit out the slab, okay? So you don't have to cast it into an ingot first and then go ahead and bring it into an intermediate shape. Now, over here, you have what's called strip casting, essentially the same thing, except you are making very, very, very thin strips. Okay, so this is just an explanation of what I talked about before. You have molten metal from a reservoir fed straight through and cooled right here, and then emerges as a continuous strand. That's why it's called strand casting. Now, let's take a little break and talk about the recrystallization that we mentioned to you before. And we're using the rolling process as an example. Okay, so what occurs during the recrystallization process is that as your metal goes through these rollers or as your metal is worked, the crystals or the grains, or what's called, they kind of reorganize. Now, exactly what are these grains? So here's a diagram representing the grains, which are groups of molecules that are aligned in different ways. So this would be considered a grain here because you have groups of molecules aligned kind of slantwise. This will be another grain or crystal because you have groups of molecules aligned kind of slantwise the other way, and then you have groups of molecules kind of aligned horizontally, so they're aligned in another way too. And all these boundaries occur where these groups are aligned in different fashion. So these are called crystals or called grains. Now, the smaller these groups are, the stronger the structure of your metal is going to be. So that's what we talked about when we mean grains or crystals. All right. So what happens when your metal is rolled near that recrystallization temperature and grains are formed, okay? These metals recrystallize. That means the crystals or the grains kind of reorganize, all right? And typically smaller grains are going to be created, but since that metal is at a high temperature, it anneals it in that process, meaning it grows these grains back to the original size. Okay. Now, what are some factors that affect the size of the grain? Well, your initial grain size. So, how big were the grains at the beginning? Grains are crystals. How much deformation occurs? Okay, and then the temperature at the end, of course. So that determines how much annealing is taking place, and then how fast are you cooling also? And so, what level, what point at which those grains are going to be locked into place? So all of those affect that rate. So let's get into the forging process. Forging is another hot working process, and you heat the metal. Of course, heating the metal creates its plasticity, how well or how easily you can form it, and then you just form it, and it can be formed in different ways. But let me give you an indication as to the forging process because it is one of the stronger working process. We'll talk about hot forging in this presentation, but we'll also talk about cold forging later on in another presentation. Now, forging in general gives the metal your highest static fatigue and impact strength out of all the hot working processes. So if you want a metal to have a very, very strong structure, then you want to go ahead and forge it. And here's a little comparison of the cold forging, hot forging, and machining processes. And so it says that forging will give you a better grain or crystal flow, and that means that it allows all those different groups of organized molecules to be together in a continuous flow, all right? So this one is the best. Cold forging actually will give you your maximum strength. We're talking about hot forging. So you see this flow in hot forging, it's cut off a little bit more than cold forging, but it's still smoother, much smoother around the edges than as far as machining. So machining, you see the flow, when you machine the process, it aligns everything and doesn't allow the crystals to flow around the edges. So that gives you the lowest strength out of all of these three. Okay, so what type of forging machines do we have? Okay, I just thought this picture was kind of cool. But forging process, you think about, hey, we have a blacksmith, he has an anvil, he's beating it with a hammer. That is a forging process. But forging process also includes other type of machines. So you have an open or a die drop forging machine. That's an open die drop forging machine. Um, you have what's called an impression die drop forging machine, and then we'll talk about press forging, swaging. We don't upset forging is simply upsetting or deforming it, but we'll talk in detail about numbers 1 through 4. So there's a machine called a drop hammer forge. Now, what is that?
Most forgings are made in drop hammers. One widely used type is the board drop hammer.
This is a drop hammer
It
forge.
gets its name from the hard maple boards that are attached to the ram. At the top of the frame,
We're not going to watch this entire video, just the beginning of it, and then I have this video posted in D2L so you can watch the rest of it at your leisure. This video is about 4 minutes and 27 seconds long, but we'll just watch the first couple of seconds.
They pass between, but do not quite touch, continuously running rollers. Whenever the ram has fallen to deliver a blow to the work, the rollers automatically press against the boards and drive them upward, carrying the ram up to its top position. Then the boards are caught and held by wedge action until the hammerman releases them for the next blow. This cycle will repeat itself automatically as long as the treadle is held down. This hammer is rated at 2,500 pounds, that being the weight of the ram. Board hammers run up to about 7,500 pounds and make forgings up to about 30 pounds. Another kind of gravity drop hammer is the airlift hammer. Instead of boards to raise the ram, an air cylinder and piston do the work. Operating the treadle lets the ram fall freely of its own weight.
All right. So we're going to let you watch the rest of that upon your own leisure, and let's keep going. All right. So if you continue watching that video, it talks about how you can have steam or air pressure. The last I mentioned air pressure used to raise a hammer, and it can be either dropped or forced down, kind of hammered down onto the heated metal. Okay. Now, you can have different types of forging. So that was an example of a drop die forging, what kind of hammers down in it. You can also have what's called open die forging. And so in open die forging, you have the metal that's really squeezed, or it can also be hammered down to increase its length or decrease its cross section. So the reason why it's called open die is because you only have the die on the top and on the bottom, and then the sides are completely open. And so usually these are used to, as I mentioned to you before, decrease the cross section. That's supposed to be an O typo there. Decrease the cross section of a particular, it could be either intermediate form or a lot of times it's an ingot. And usually this can be done to very large pieces. And so this could be actually connected to a forklift or a very large machine holding a very large piece here. Usually this does require a lot of skill, okay, to make sure you give just the amount of force to create the shape that you really want. Then we have what's called impression die forging. And impression die forging is where you have the metal that's shaped by an upper and lower die. So the sides aren't out. And this gives you some advantages. You have better repeatability, and oftentimes you do have progressive dies used as I can't remember if I mentioned that before, but progressive dies are when you form it a little bit, then form a little bit more, and form it a little bit more, something similar to what you saw in that tandem mill stand. When you have a die forging here, an upper and lower die, as I mentioned to you before, oftentimes there's an area here called flash. So to make sure that you have enough metal to fill the entire die cavity, you have a little bit of a space right here. You put more metal, just a little bit more metal than you really need. And that metal goes into the space right here. And that's called the flash. And the flash is separated into a saddle. And then you have another part of it that's called the gutter. We'll look into a little more detail in just a while. So this is an example of the process of forging. In this case, though, if you look closely, you see that there's no flash. And so you do have flashless dies where you are supposed to put in the exact right amount of metal, and then it's formed to the die, and then that's it. So this is another video, but I am not going, it's going to talk about open and closed dies. I'm not going to watch this whole one either, but this one is also posted for you in D2L.
Piece by high velocity impact, or presses, which deform the workpiece through controlled high pressures. Forging is one of the oldest metalworking processes, dating as far back as 8000 BC. It is utilized today to reduce the cross-section. improve the metallurgical microstructure, provide directional grain flow, and eliminate porosity of cast ingot in fabricating wrought mill forms, and to form discrete parts to near net shape from these wrought mill forms, further refining microstructure and directional grain flow. Because of these effects on microstructure and grain flow, the mechanical performance of wrought mill forms and parts is typically superior to that of cast metals. Open die forging is performed on ingot, billet, bar, or a preform, and is the deformation of a workpiece between flat or shaped dies without completely restricting metal flow. This deformation can result in lengthening of the workpiece while reducing its cross-section, upsetting regions along the length to greater sizes than adjacent regions, or bulging the workpiece's cross-section while reducing its length. Lengthening and upsetting are typically done using multiple impacts, as the workpiece is incrementally advanced lengthwise and rotated about its longitudinal axis. There is essentially no limit to the size of forgings that can be made using open die forging. They can range from a few centimeters to 30 meters in length and weigh from a few to up to several 100,000 kilograms. Although fairly complex shapes can be made using open die forging, most are rather simple solids or hollows requiring considerable machining to achieve final shape. Forgings are produced using simple flat, V-shaped, or semi-round dies.
All right, so again, you can continue watching that video on D2Well, and I'm going to keep going on with the rest of the presentation. All right, so it did mention to you the difference between your drop hammer forges and then your presses. And so your press is really going to do more of a squeezing action rather than a hard striking of the metal. And you have some different advantages to this. But here's one type of press called a mechanical press. And mechanical press compared to drop forging machines, sometimes it can give you a problem with jamming of the ram at the bottom, but they operate more quietly. They allow more accurate control, and they produce a higher force and energy, okay? So they work better when you need parts with a closer tolerance. Now, you also have fewer blows required per forging, so that's good. Less operator skill is needed, okay? And remember I told you before, it's a squeezing rather than a striking of the metal. Now, shorter forging to die contact is good because it extends the life of the die. That means that die is contacting very, very hot metal, and so you do have some temperature effects that will wear that die down. So the less amount of time it contacts the metal to go ahead and forge it is always going to be better. And so here's a picture of a mechanical example of a mechanical press. You have other presses. So here's a vertical screw press. So the difference between this is that you have this vertical screw action. And so here, instead of your flywheel, mechanical press uses a flywheel to transfer the energy. This uses kind of like a vertical screw mechanism to do that. And because of that, you have a uniform force throughout the stroke, unlike the drop hammer. So that's very good because a uniform force throughout the stroke gives you more uniform properties from formation of the metal. Then you have a hydraulic press. Your hydraulic press is going to be the one that delivers the highest forces, but the disadvantage is that it's going to be very, very slow. And that's, in general, for hydraulics, you have higher forces, but it just acts really slow, okay? And so if you have extremely large forgings that need very, very high forces to be shaped, then this is what you would use, a hydraulic press. So here's some examples of hydraulic press here. You can see they're really, really huge. Here's a hydraulic cylinder pressing down, can deliver extremely, extremely high forces. All right, now remember that your forging dies come into three groups. We talked about open die forging, okay, where your forging is being pressed on top and the bottom, and it's open in the middle. That's why it's called open die forging. We talked about impression die forging. Impression die forging, or closed die forging, here we'll have a top die and a bottom die. So it is enclosed. And oftentimes you'll have this area over here, which is called the flash, which is used for the metal to go to make sure that it fills in that whole die. So you usually put in just a little bit extra, and you need to have a space for that to go. So that goes right here, comes over what's called the saddle, and then goes into this area that's called the gutter. And this flash is machined off later on. Then you have what's called flashless dies, where you don't have the flash area. You put in the exact right amount of metal so that you don't need that flash. The swaging or swagging process is actually really interesting. It involves a rotating spindle, and then you have that between cylindrical rollers all in a ring. And what happens is that typically it's used to reduce a cross section of a tube. So you'll feed that tube through, and as it rotates, these little hammers are rotating around and they hit rollers. And when they hit the roller, they hammer down onto the tube. So here's kind of like a isometric view, and then here's a kind of a cut cross-section view. You're feeding the tube through, and these hammers, they hammer in as they hit on these rollers here. And this is another cut section. So the tube goes in the middle here. Here are your hammers. As they hit these rollers, they hammer in onto the tube. Here's another diagram of it. So here are your hammers right here. As they spin, they go through spaces where they don't hit the rollers, but when they hit the rollers, they come in and they hit the tube that's inside here. So here's another video that just kind of shows you how that happens. I'm not going to show this entire video. It's 2 minutes and 42 seconds.
Two-bed forming machines or swagging machines purely operate on a cold process.
Okay.
Hence, they consume less power, making them highly suitable for industries for mass production of swaged parts.
You have to forgive the kind of monotone voice of this video, but I do think it's very informational.
Rotary swaging, also known as radial swaging, is often a cold working process used to reduce tube diameter, produce a tapered end, or to add a point to a round workpiece. This type of swaging machine uses 2, 3, or 4 dies that hammer up to 2,000 a minute. Dies are mounted on the machine spindle, located inside a cage containing rollers, which is rotated by a motor. As the spindle spins inside the rotary swaging machine, the dies push out to ride the cage by centrifugal force. When the dies cross the rollers, they push the dies together due to their large size. Like tube swaging, rotary swaging can also create an...
All right, so that's about enough I can have that monotone voice, but it does give you an indication of how that process actually works. The extrusion process is another hot working process, and you will find later on that a lot of these processes are really repeated in cold working, but just under different conditions. And so in extruding, what you're doing is you're forcing metal through a die. It's kind of like toothpaste from a tube. So here's an example of extruding. So you can see here, you have your ingot form there, and then it's being pushed through here, and they'll show you the other side in just 1 second as it's extruded. So push it through, and there it's being extruded out. So it went through that die. You can see it now has a special cross-sectional area. Okay, so there are advantages. So you can make intricate cross-sectional shapes. That's an advantage. The disadvantage is that it's more expensive than rolling. Okay. So there are two types of extrusion process. There's direct extrusion, where you just have a ram, you have the metal, whether it's an ingot or a billet, pushed through a die. And in this case, there are some disadvantages here, and that's because of the way it's set up. You have a lot of friction between the billet or the metal and the container, which can cause non-uniform work on the metal. All right. And so then they've developed this indirect extrusion process to kind of address those issues. In this case, you have your ram and then it's being pushed through, but the die is actually on the inside of the ram. And so the metal doesn't come out on the other side. It goes back through the middle of the ram where the die is. So you have some advantages and disadvantages of this process as well. Disadvantage, of course, is your extrusion has to be small to kind of fit in the middle of your ram. But advantage is that the work is imparted in a uniform way, and that helps to make dimensional control better. So you have direct extrusion and then indirect extrusion we're talking about. Another process is called hot drawing, where instead of pushing it through, you actually pull it through a die. Okay, so extrusion, you push the metal through a die. Drawing, you pull the metal through a die. Here's an example of the drawing process, hot drawing process. Okay, so here you have your bloom, okay? And what you're gonna do is you're gonna take, and first of all, you kind of feed it through with this little gripper. You grab the end of it, and then as you go through the die, it reduces the size of this particular tube. Now, this mandrel is meant to kind of maintain that hole in the middle, okay? But this is one of the ways of, like I told you before, is you're pulling it through the die, okay, instead of pushing it through. So that's the drawing process. You pull it through. Another hot working process called hot spinning, which is interesting. It kind of reminds me a little bit of kind of shaping that clay, like pottery, shaping pottery, because you have metal spinning, and then as it's spinning, you have something come through, and then you shape it. Now, remember, this is hot working, and so you have it heated to a high, close or over its recrystallization temperature, and that allows you to go ahead and shape it. Okay, so shaping a flat or preformed metal disc over a rotating form. Sometimes it's a metal disc, or in this case, I'm about to show you this video, it's actually just the end of a pipe. And so hot spinning can be used to make solid ends of pipes, or to close and make tanks so that you don't have to create a separate top for it. Makes it a lot stronger. But here's the video for that. So this is actually just the end of the pipe. Here, you're heating right here, only the end of the pipe, and this is the rest of the pipe right here. And you're kind of shaping it and forming it to close the pipe. You don't have to create these separate caps, and that makes it stronger, that you don't have to weld a separate cap. And there you go. So this has been the hot working process. If you guys have any questions, you can always email me and ask me questions. But I hope you have enjoyed the presentation.